Hi. In our earlier videos, we covered some of the basics about how to use the Vernier Lab Quest for measurements, and we began studying how to use the dual range force sensor. And what we're building up to is we're trying to impart students with the knowledge, skills, and abilities to build or to use something like our force plate. And the force plate is composed of 3 individual dual range force sensors, and in this case the whole is very nearly the sum of its parts. So when you ask yourself, well, why are we spending so much time studying and learning about the single dual range force sensor, it's very simply because once there are 3 of them, we need to be able to understand what each component of the system is doing individually, because the force plate has the 3 force sensors, and so it's 3 times as complicated. So we're going to build our skills on the single force sensor first. Keep it in mind that our accuracy goal is force measurements, thrust measurements for model rockets with an accuracy of 1% or better. So one thing, well, a couple things that we didn't talk about yet that I want to talk about is that we use the force sensor in the previous videos by hanging something from the hook, and I also want to demonstrate that it can be used also not just with a pull force, but it can be used in a push force mode as well. So if you essentially orient it so that the sensor part is upward, take the hook off, it just unscrews. Now it will measure a downward force that might be applied to the hook, and it's calling the downward force, in this case, negative, the push force. Alright, so let's try and calibrate it again now that the switch is properly set for 10 newtons. Experiment, calibrate, calibrate LabQuest 1, the 10 newtons. Calibrate now, and we take the mass off, so 0 newtons. And now let's go ahead and, this is a 100-gram mass, so with gravity it exerts a force of 0.98 newtons. Press keep, press done, and now we can see that the force we're measuring is very close to 0.98 newtons. We can collect for our 10-second collection time, and then we can look at the statistics when it's done and see how close our average is. So the mean is 0.9825 newtons, and if it were perfect it would be 0.980, but we've got about 2.5 parts in 1,000 error, so that's 0.25% is the error in this case. Let's also do a little reminder here as far as the data collection, because we didn't open up a file that had been saved before, and it kind of defaults for this sensor to 50 samples per second, and we like to run it at 1,000 samples per second because that's the preferred collection rate for doing model rocket thrust. So we can also re-zero it now that the mass is off of it. So if we do a scan without any mass up there at all, the mean value, you can see that the instantaneous values are bouncing around a little bit, but the mean value should be very close to 0, and here we have 7 parts in 10,000 approximately for the mean, and it's negative. So then if we put the calibration mass back up there and we run it, it should come out to be, and the instantaneous values bounce around a little bit with experimental noise, but the mean should come out to be very close to 0.98, and in this case it's 0.09843. Okay, so that's just a re-demonstration of the calibration and the idea that it could measure a push force, a downward force, as well as a hanging force. But let's go ahead and let's reorient it this way, because I also want to demonstrate some things about the larger range, or the 50 Newton range on the force sensor. So turn it upside down, or back in hanging mode, switch it over to 50, and let's see if we can get it, use sensor setting here. But now if we just, if we run it, we're probably in a situation where we need to calibrate it again, because there's nothing hanging, and yet we can see we have 0.27 newtons when it's just sitting there, and that might be approximately the downward force that the hook is giving it. But let's think about how to calibrate it properly. And to demonstrate the calibration procedure, what I've got here is I've got a precision market scale. It's actually made for selling produce. It's accurate to 5 parts in 1,000 of 1 pound, or 0.005 pounds. And just to, before we use it as a standard, because we're going to weigh our calibration weight on it first, let's just verify with these weights here. Each of these weights is 100 grams. And if you remember, a kilogram is 2.205 pounds. So 100 gram mass should be 0.220 pounds. And indeed, the 100 gram mass is, I don't know if you can see that, it's reading 0.220 pounds. And then another 100 gram mass brings it up to 0.44 pounds. And another 100 gram mass brings it to 0.66 pounds. And we only have 300 gram masses in the laboratory today, but we also have a 50 gram mass, and that's half of a 100 gram mass, so it should add another 0.11 pounds to bring it up to 0.77. So we can see that at least with these small laboratory masses that are intended to check and to calibrate more precise analytical balances, the market scale demonstrates a very nice accuracy. And so now, because if you recall, one of the things you want to do when you're calibrating something accurately is you want to use a known weight or a known mass, and it needs to have about the same full scale as the thing that you hope to measure. So this is it's advertised to be a 5 pound weight that would go on a barbell, but when we weighed it precisely, and we've been using the same one for years, when we weigh it precisely, we get 0.4875 pounds, and we've computed that to be 21, hopefully you can read that, 21.685 newtons, because this is just sort of a laboratory standard. We carted around with us when we were measuring fish, and we use it to check, for example, the calibration and to make adjustments to the readings on hanging scales that are used for fish in cases that the fish are too heavy to weigh on the market scale. Alright, so going back over here, we're calibrating the dual range force sensor now for larger weights. So go to experiment, go to calibrate, calibrate now, and with nothing hanging from it, of course, it's 0 newtons. And then it's going to be 21.685 newtons. And this is kind of heavy here, so we just need to take care that we don't pull anything over or break anything. So hanging the mass there, we can now tell it to keep the 21.685, and now we can be done. So now when we scan, go ahead and erase and continue, because we don't really need to save that last reading. It's just scanning across, then it's going to pop up the average, and it comes up with the mean value is 21.68, so has excellent accuracy there.